Hi everyone. Today I'm going to try to sell jamming for different kinds of sort of shape change and shape morphing concepts. Specifically, I'm going to focus on things I think that we haven't been leveraging so much that jamming has to offer. So it'll be a little bit of jamming mechanics and a lot of sort of deformation and shape morphing. To do that, first I have to introduce what jamming is. I'm going to start with a very simple jamming structure. I'm just going to take some sheets of material. I'm going to put it in an airtight envelope, and I'm just going to attach it to a vacuum. To quickly show what this looks like in reality, some shadow here. And here, as you can see, the only difference between the right and the left, have I turned the valve to the vacuum off and on. Quite dramatic change in stiffness. You might be familiar with these things. How does this work? In the unjammed state, the layers can freely slide with respect to each other, so now they can sort of independently move. Once I jam it, I squish it really tight, create frictional coupling in this case. It could be kinematic coupling as well in other cases, and I create this cohesive structure. And it starts acting like this big bulk rather than individual parts. If you want to imagine what it might feel like, think of having like 30 sheets of aluminum foil or an aluminum sheet that has the total thickness of 30 sheets of aluminum foil. So you can sort of transition between all of those things. To quickly look at this in a force deflection plot, we have this very dramatic change in stiffness. We can program it based on the geometry of my structure. And this helps with shape locking. So this has been used in different cases. So here you're seeing in the soft state, you put your structure in a certain state, and then you stiffen it, and it keeps the original shape. So that's one, and I think that's the most commonly used type application for jamming and shape morphing. But there's a few other things that jamming has to offer that we can use. So in the jam state, if I continue to load a structure, it will start slipping. And this happens when the shear stress, in this case along the layers, exceed the amount of friction force between them, which I can tune with the pressure. And if I do the unloading, as you can see, I have some area under the curve, which means I have plastic deformations. So to quickly show this, how it works. So here again, it's just sheets of paper in a bag, and I can really nicely plastically deform it. And then when I unjam it, it resets back to this original state. Why might I want plastic deformation rather than elastic? This time you can do a lot of local shape changes that you might want, right? Versus in this case, you want the whole thing, because it's all elastic, you really need to hold each part of the structure to be able to lock it. In this case, you can sort of make really small changes, kind of like the clay example someone gave earlier today. I want to highlight a few of the other advantages. One, you can change at which force you're starting to deform your structure. So just by, in this vacuum actuated case, just by lowering the vacuum pressure, you can change at what point you're going to start plastically deforming. And then in this case, and you can even do this locally in different kinds of structures. And so you can change, again, how you're going to deform. And the other nice thing is, so this curve is very similar. If you bent like a paper clip, it would also show this kind of blue curve-like behavior. The nice thing is that you can unjam it to reset, right? So you have this really nice tunable as well as reversible plasticity that you can use. So far, I only started with layer jamming structures, but you can jam other geometries, which allows you to create different kinds of morphologies and different levels of performance. So layers, as I showed, you can jam fibers, grains, or you can design the constituent geometry that you want for your desired application space. If we just take a very sort of dumb high-level approach to this, we can kind of get an idea that in layer jamming structure, we're mostly going to deform in this 1D curvature. Fiber jamming, I can sort of follow a more 2D trajectory when I'm deforming. And in granular jamming, then one of the most famous examples is the universal gripper, right? Coffee grounds in a balloon. And here you have this 3D conformability. But there's something a little bit more than that. So here, this is very bulk behavior, but it really changes how, is your deformation elastic or plastic, what the deformation mode looks like, changes on your loading condition. So are you twisting it? Are you stretching it? Are you bending it? So that's what we kind of need to look at to understand. So we need to look at all the sort of, these are the fundamental loading conditions that could be happening. And we look at these elementary jamming structures and see how it might behave. And to understand this, we look inside the jamming structure. Basically, how the deformation behaves depends on how these things move with respect to each other. Are they sliding? Are they rearranging? In what dimension are they sliding? In what dimension they're rearranging? And that overall changes the behavior. So now we need some kind of taxonomy, a way to describe the different interactions between the individual parts to get a sense of the overall global deformation mode. And to do that, I'm going to define 4 deformation modes, and these are going to be all the 4 possible things that could be going on inside a jamming structure. The first one, I already introduced this before. Things are locked until a frictional threshold is exceeded, and then they start sliding. So this could happen in bending structure or things like friction clutches, for example. This kind of behavior exists here. And here, the thing I showed, that you have this really nice, clean, elastic regime. and you can change at what point you're transitioning to the plastic regime. So this could be quite advantageous. The second one is kinematic. So this could be granular jamming structures, or this could be fibers along one dimension, right? And here what's happening is they're rearranging with respect to each other. If we consider a lot of assumptions, let's say they're all rigid parts and the encasing in this case doesn't have too much elastic spring back, the deformation here is mostly plastic. So for example, if you want to tune at what point you're becoming plastic, or you want to have a non-plastic deformation mode, kinematic is not really what you want to do. But you might want to start deforming in 3D, so that might be something you want. The third and most boring one, you're just squishing something onto itself, so the jamming doesn't have an influence, doesn't do anything, but we have to cover it. And then lastly, actuation. So you're opening this, you're stretching thing apart. So in the vacuum actuated case, what happens is the bag wants to compress because there's a vacuum applied. So the shape of what you have inside doesn't matter so much. It's basically the actuation method. And here, the deformation is mostly elastic, so it goes back to its original state. And then now I understand all these deformation modes, and I can sort of fill this table, and now I have a really nice understanding of which ones can plastically deform, and then I can really start modeling the force deflection curves and then program my structures into that. I won't go into the details of this sort of more specific modeling, but I'm going to show a case study just using the more qualitative assessments that we can get from such a taxonomy approach. And for that, I'm going to do a case study. As an artist, as you introduced me before, this is a nice example for me because it's a mold making sleeve. So the idea is as follows. I'm going to have a sleeve, and I want it to be reusable, and I want to make a mold from it. First, I want to deform to my object, which means I need some kind of 3D conformability, and I need softness. So I need it to get into all the nooks of my object, right? And here, as I kind of mentioned, you probably want granular jamming so you can get into all the corners. Then though, so I have my object in it, I conform nicely. What do I want to do? I want to stiffen it. I want to open the sleeve, I want to remove my object, and I want it to go back to its original state. So I need some elasticity. And hopefully I was able to communicate so far that if you want elasticity, you don't want any kind of kinematic deformation mode, which exists in fiber jamming and granular jamming. So in this case, you would ideally want to use layers. Finally, I have my structure. I poured some casting material in it. I waited for it to cure, and then now I want to remove. I again want to be soft and 3D conformable because I don't want to chip certain parts of my object if I'm sort of opening it up in a certain dimension. To quickly show that I'm not lying. So here you're just seeing paper in a bag again. You see this nice, really elastic regime that's springing back. Here, it's the granular jamming. You can't really see from this camera view, but I'm making my fingers making little dents into the coffee grounds, but it keeps opening more and more. In this case, I have this much stiffer structure because I have more material, but now I have this nice elastic spring back, and I have conformability on the inside. So basically, the idea is to combine both of them. You keep the global shape memory from the elasticity from one, and you take the local shape memory from the 3D conformability on the inside, and then you have your mold making sleeve. So let's quickly show how it works and if it works. And for that, what I did 3 experiments. I did a mold making sleeve just of this, and of the hybrid to compare the different results. And I used a squash from the grocery store to mold. So let's start with the worst one. I promise it's going to get better. So now I just used a sheet of layers. It's awful. It doesn't look like a squash at all. It's really bad. But it conforms to the overall environment. Just to show you, this is the resulting cast made out of plaster. The blue is a 3D scan of the outer surface. The white is a 3D scan of the original squash. And the bottom is just showing where the errors are concentrating when I compare the point clouds that I can take. Now let's do just grains. Okay, it's a little better. Now I can sort of see the squash shape, but hopefully you can see that it's a sort of stretched out squash. Why? Because when I was trying to remove the squash, it didn't spring back to its original state. If I combine both, I get the best of both worlds, right? So it snaps back to its original shape and also keeps the local shape here. And I think interesting thing to see here, of course, these are a very quick proof of concept. A lot of things could be improved, but the error of these two are actually quite similar when I compare the 2 different shapes versus this one. So it's like, even though this looks better, mathematically, it's actually not as much better. So that's one case study, but again, if you kind of think about the different kinds of plastic, elastic deformations you might need in different dimensions, we can collaborate maybe and make some jamming shape morphing structure. Thank you so much for your time.